In some regions of the universe, galaxies appear to thin out so dramatically that entire sections of intergalactic space seem almost empty. Current cosmological models predict uneven distribution across large scales, but not vast isolation zones where visible structure appears to collapse beyond expectation. Cosmic voids are not completely empty regions. Even in low-density areas, gravity should still leave behind traces of galaxies, dark matter structures, and residual clustering spread across intergalactic distances. Large-scale simulations of cosmic evolution suggest that matter should organize into a connected web rather than disappear into sharply underpopulated regions. What makes these voids unusual is not merely their size, but the degree of absence they appear to contain. Some observed regions show galaxy populations falling far below what current distribution models would normally predict, creating the impression that entire sections of cosmic structure may be missing rather than simply sparse. That distinction matters because standard structure formation depends on gravity amplifying small density variations over billions of years. Even regions that begin with lower matter concentration should still retain enough gravitational interaction to preserve detectable galactic presence across intergalactic scales. Instead, observations suggest that some isolation zones may have undergone a far more aggressive density collapse than expected. The visible matter distribution appears to thin out beyond normal statistical fluctuation, leaving regions where large-scale structure becomes difficult to reconcile with surrounding cosmic patterns. The anomaly becomes more difficult to interpret when these voids are mapped against the broader cosmic web. Filaments and galaxy clusters remain interconnected across enormous distances, yet certain regions appear disconnected from that network with unusual sharpness, as though gravitational organization weakened unevenly across the same universe. One possible explanation is that the observed emptiness may not represent true absence, but incomplete observation. Extremely faint galaxies, diffuse matter structures, or weak gravitational signatures could exist below current detection thresholds, creating the appearance of disappearance where matter remains partially hidden. But that possibility introduces a measurement boundary rather than resolving the anomaly. If missing structure exists beyond observational sensitivity, then current galaxy surveys may be systematically underestimating matter distribution inside these regions, leaving the true scale of the isolation uncertain. The problem is that multiple independent surveys still reproduce similar low-density patterns across enormous distances. Different instruments and mapping techniques continue to identify regions where visible galactic structure falls dramatically below surrounding cosmic averages, suggesting that the effect may not be entirely observational noise. That creates a conflict between expectation and observation. The large-scale universe is generally modeled as statistically homogeneous across sufficient scale, yet these extreme void regions appear to introduce local conditions where structure formation behaves far more unevenly than expected. Some cosmological interpretations suggest that dark matter distribution inside voids may differ from visible matter distribution. Galaxies could become rare, while underlying gravitational structure remains partially intact, allowing large regions to appear empty without fully lacking mass. Yet even that explanation leaves an unresolved gap. If dark matter remains present inside these isolation zones, current models still struggle to explain why visible galaxy formation would collapse so dramatically, while neighboring regions continue forming dense interconnected structures. The uncertainty deepens when considering how these voids evolve over cosmic time. Gravity normally pulls matter toward denser regions, gradually evacuating low-density zones. But the observed scale of some voids suggests evacuation processes that may exceed what standard evolution models cleanly predict. The expected outcome would be gradual thinning. What appears in some observations instead resembles accelerated structural emptiness, where galaxy density falls so low that portions of intergalactic space seem almost detached from normal cosmic organization. That apparent detachment creates another observational boundary. Void interiors contain fewer luminous objects, which also means fewer measurable reference points for studying their internal structure. The emptier the region becomes, the harder it becomes to determine whether the observed absence reflects true physical isolation or incomplete visibility. This creates an evidence gap at the center of the anomaly. Scientists can map the boundaries of many voids using surrounding galaxy distributions, but understanding what exists deep inside them becomes increasingly difficult precisely because detectable structure is so limited. The situation becomes more unstable when scale is considered directly. These are not local gaps between galaxies. Some void regions extend across distances so large that light itself requires hundreds of millions of years to cross them, turning absence into a dominant intergalactic feature rather than a small irregularity. At those scales, statistical explanations become less comfortable. Random fluctuation can produce sparse regions, but the larger and emptier these structures appear, the harder it becomes to determine whether current cosmological assumptions fully account for their formation. One interpretation is that current simulations may underestimate how aggressively matter redistribution operates across intergalactic environments. Another is that unseen mechanisms influencing structure growth remain partially hidden inside the evolution of the cosmic web itself. Neither possibility closes the anomaly. Improved simulations still depend on incomplete observational inputs, while observational surveys remain constrained by the difficulty of detecting faint structure inside regions already defined by extreme absence. The contradiction is subtle but persistent. The universe appears structured enough to produce enormous interconnected filaments, yet simultaneously capable of generating regions where that same structure nearly vanishes across incomprehensible scales. That imbalance leaves a remaining uncertainty at the core of the phenomenon. If these voids represent natural outcomes of known cosmological evolution, current models may still be missing critical information about how matter distributes itself across extreme intergalactic distances. And if the observations are incomplete rather than physically extreme, then some of the largest structures ever mapped in the universe may also be among the least understood, because the deeper the isolation becomes, the less evidence remains available to explain what is actually there. The deeper problem is that void behavior does not remain isolated inside the void itself. Matter redistribution across intergalactic space affects how surrounding filaments grow, how galaxy clusters accumulate mass, and how gravitational structure propagates outward across enormous distances. In standard cosmological evolution, low-density regions gradually transfer matter toward denser boundaries. Over time, this should sharpen the contrast between void interiors and surrounding galactic walls. But some observed isolation zones appear so underpopulated that the evacuation process itself begins to look disproportionately efficient. That efficiency creates a scaling problem. If matter evacuation becomes too aggressive across sufficiently large regions, then current assumptions about how evenly structure evolves over cosmic distances may no longer remain stable under extreme conditions. The anomaly becomes harder to constrain because structure is inferred indirectly rather than observed completely. Galaxy distribution acts as a visible tracer for underlying matter organization, but inside extreme voids, the tracer itself begins disappearing, leaving the deeper structure increasingly uncertain. The emptier these regions appear, the less reliable direct reconstruction becomes. That limitation affects more than visual mapping. Cosmological models rely on statistical distributions of observable galaxies to estimate how matter behaves across intergalactic scales, meaning that unusually empty regions may distort assumptions about the balance between visible structure and hidden mass. One interpretation suggests that current surveys may be detecting the visible outcome of much larger underlying density fluctuations. Small deviations present in the early universe could have amplified over billions of years, eventually producing regions where galaxy formation became progressively suppressed across enormous distances. But amplification alone may not fully explain the sharpness of some observed boundaries. Certain void regions appear to transition from normal cosmic structure into extreme sparsity faster than gradual density decline would normally predict, creating edges that look unexpectedly severe at intergalactic scale. That creates an analytical tension inside the evidence itself. If the boundaries are physically real, then structure formation may behave more unevenly than expected under extreme low-density conditions. If the boundaries are exaggerated by observational bias, then current mapping techniques may be amplifying absence where incomplete visibility already exists. Neither interpretation cleanly removes the anomaly. The uncertainty grows when propagation effects are considered over cosmic time. Once a region becomes sufficiently underdense, gravitational attraction weakens locally, reducing the probability of future galaxy formation inside the same region. That process may reinforce emptiness over billions of years, turning sparse zones into progressively larger isolation structures. In that sense, absence may propagate structurally rather than remain static. The result is a feedback condition where low-density regions become increasingly resistant to rebuilding visible structure. Matter flows outward toward denser regions, while the interior continues losing the gravitational conditions needed to generate substantial galactic recovery. Current models can simulate portions of this behavior, but the farther the process extends toward extreme scales, the more sensitive the outcome becomes to initial assumptions about early matter distribution. Tiny differences in primordial density may eventually produce radically different large-scale structures billions of years later. That sensitivity creates another evidence boundary. Scientists cannot directly observe the universe's earliest density configuration with complete precision, meaning the starting conditions behind modern void formation remain partially reconstructed rather than fully measured. And reconstruction becomes increasingly unstable when applied across regions already defined by missing structure. The scale escalation becomes difficult to intuit because these voids are not isolated gaps surrounded by otherwise simple geometry. They exist inside a dynamic cosmic network where structure evolves unevenly over immense spans of space and time, allowing local absence to influence neighboring formation patterns across intergalactic distances. As voids expand, surrounding matter concentrations may become denser by comparison. Filaments sharpen, galaxy walls grow more pronounced, and the visible contrast between populated and underpopulated regions intensifies, making the universe appear simultaneously more connected and more fragmented at larger scales. That fragmentation introduces a deeper contradiction. The same gravitational evolution responsible for building enormous coherent structures may also generate regions approaching near structural emptiness, as though cosmic organization and cosmic isolation emerge from the same underlying process. The anomaly no longer appears limited to missing galaxies alone. It begins affecting how the universe organizes visible structure across scale itself, raising the possibility that current large-scale models describe average behavior correctly while still failing under extreme distribution conditions. Some void regions may therefore represent boundary cases where cosmological assumptions become difficult to test cleanly. Observable structure becomes too sparse for direct internal measurement, while surrounding regions continue evolving normally enough to preserve the appearance of overall stability. That imbalance makes the phenomenon unusually resistant to closure. The deeper observations extend into these isolation zones, the more the anomaly shifts from a question of where are the galaxies toward a more difficult uncertainty, whether the universe distributes structure in ways that current observational density models still only approximate rather than fully explain. And because the regions themselves contain so little detectable structure, the evidence required to resolve that uncertainty may remain trapped behind the very absence that defines the phenomenon in the first place. What these voids ultimately reveal is not that the universe lacks structure, but that structure may behave far more unevenly at extreme intergalactic scales than current models comfortably describe. The broad framework of cosmic evolution still explains how galaxies cluster and filaments emerge. Yet inside these isolation zones, the same framework begins losing precision as visible structure approaches near absence. The anomaly no longer rests solely in the emptiness itself. It emerges from the fact that modern cosmology can successfully model the large-scale universe overall, while still struggling to explain why certain regions appear to evacuate visible matter so aggressively without fully breaking surrounding structure formation. That leaves a boundary condition current observations cannot fully cross. The deeper scientists attempt to study these regions, the fewer detectable signals remain available to reconstruct what exists inside them, forcing cosmological interpretation to depend increasingly on indirect inference rather than direct measurement. And that creates the unresolved limit beneath the entire phenomenon. The universe may contain regions so structurally empty that the evidence needed to explain them becomes progressively harder to extract from the emptiness itself, leaving some of the largest observable features in existence defined less by what is present than by what appears to be missing.